campus and C&EN.
That's Manny Marone, lead production editor at C&EN and occasional host of science-themed pub trivia. A few weeks ago, he hosted an afternoon of pub trivia put on by C&EN and ACS on campus during the American Chemical Society's 2019 Spring National Meeting in Orlando, Florida. ACS publishes C&EN. I'm Kerri Jansen. This episode of Stereochemistry isn't about that pub trivia night, but it does draw inspiration from it. Chemists everywhere are celebrating 2019 as the International Year of the Periodic Table. In Orlando, about 100 participants took their best shot at a slate of trivia questions inspired by the 118 elements that currently grace the iconic table. The event was full of obscure facts, spirited debate, and a blinding glare from Manny's red sequined jacket. A handful of the trivia questions were about the people behind the periodic table as we know it, the ones responsible for synthesizing some of the heaviest elements we know of, located in the last row of the periodic table. We wanted to know more about these scientists and these elements. We're talking elements with atomic numbers in the triple digits. That's more than 100 protons crammed into a single nucleus. These are elements that do not occur naturally. They're made using specialized materials in a particle accelerator, and many last only moments before falling apart. That makes them incredibly hard to study, and yet for decades, scientists have been working long hours and sifting through heaps of data in their pursuit. Often, the scientists find nothing, but in rare cases, they see a flicker of something that has never before existed on this planet. In this episode, we'll hear from some of the scientists whose work has produced these rare moments of discovery. We'll start a half-century ago, before the internet, before humans set foot on the moon, but I think after the invention of pub trivia. And we'll track the story of these superheavy elements through time. We'll find out what keeps these scientists going in the face of grueling hours and unpromising odds, and what it takes to make a new element, an event rare and significant enough that it might one day be the subject of a pub trivia question.
All right, question 5. James A. Harris was the first African-American chemist to co-discover an element, actually helping discover 2 elements. One is element 104, rutherfordium. What is the other element that he helped discover?
Let's dig into this one. When element 104 was detected in 1969, it represented the first of a group of atoms known as superheavy elements. Elements with more protons in their nuclei than the actinide series, which top out at 103 protons. Jim Harris, a scientist at what was then known as the Lawrence Radiation Laboratory, was the only chemist listed as a co-author on the 1969 paper announcing the detection of element 104, outnumbered by physicists. To understand his contribution, we need to look at how superheavy elements are made. And I should note, many people resist using the word discover when describing the hunt for new elements, because it's one thing to discover something that was previously completely unknown, as German alchemist Heinrich Brandt did in the 17th century when he isolated phosphorus for the first time, and quite another to synthesize an element that scientists already know should be possible. But whether we call it discovering, detecting, or synthesizing, the scientific process is the same. Essentially, you take 2 atoms that have enough protons between them to add up to the number of protons in the atom you want to make, and smash those 2 together in the hopes that their nuclei will fuse. Overcoming the repelling force of protons in each nucleus requires incredible amounts of energy. So scientists use a cyclotron to bombard a target atom with a stream of projectile atoms that fly along at 1/10 the speed of light. Sounds simple enough. But nuclei are finicky things, and getting them to fuse requires exactly the right conditions, the right energy, and the right type of contact between the particles. You can think of these atoms like billiard balls. The 8 ball represents your target atom, and the cue ball represents your projectile atom. Imagine they're both lined up straight with a corner pocket. On a billiards table and in a cyclotron, the goal is to get your projectile to connect with your target, and in order to get the particular collision event you want, to pocket the 8 ball or to get 2 nuclei to fuse, a glancing blow won't cut it. You need them to collide exactly head-on. If you're me, the probability of that happening is already pretty low. If you're a nuclear scientist trying to get 2 nuclei to collide, the chances are even lower. And even when you do get that straight-on collision, the nuclei will fuse only a small fraction of the time. And so it was essential in this work to have high-quality, highly pure target materials to maximize the chances for the projectile to collide with the desired atom. That means no contaminant atoms that could interfere with your fusion process.
The probability for striking the atom is greater if you have nothing but that atom. If it's hitting other nuclei, it could create other atoms that may decay and cause secondary reactions that would interfere with whatever process they're trying to do.
That's Clarice Phelps, a member of the Nuclear Materials Processing Group at Oak Ridge National Lab, who helped purify the berkelium-249 targets used to make element 117. Back in the late 60s, Jim Harris and the Berkeley group were using californium-249 targets in their attempt to make element 104. And preparing those targets was Jim Harris's job. Purifying these materials is a tedious, multi-step process, Clarice says. And the process is further complicated by the fact that these target materials are radioactive. They will decay over time, leaving fewer of the desired atoms in the target. So time is of the essence, even when working with elements like californium, which has a half-life of a little more than 2.5 years.
A year seems like a long time, but in, making isotopes and all the preparation and all the stuff that you have to do, it's actually a very short, small window.
By all accounts, Jim was really good at making those targets, and his friends and colleagues remember him as being a positive and personable guy. Jim Harris died in 2000. I spoke with William Lester, a theoretical chemist at what is now known as the Lawrence Berkeley National Laboratory and a longtime friend of Jim's.
We first met at an ACS meeting, actually, in San Francisco in '68. A couple of black scientists in the large area, so we happened to, see each other and wander over, and began to talk. Very positive, very interesting, funny guy, good conversationalist. All those attributes which, to some extent, you don't describe to scientists.
Jim Harris is known for his dedication to outreach, often meeting with students and young people and talking about science.
He appreciated the value of being able to talk to these young people and provide guidance and so forth. It was his outgoing personality, his very positive outgoing personality. Jim was a beacon of light in many ways.
I found a photo of Jim taken in 1969, the year element 104 was announced. He's wearing a light-colored cardigan and what I now know to be an uncharacteristically somber expression for this normally gregarious chemist. And he's surrounded by the team members who together found evidence of that first superheavy element. Group leader Albert Giorso is there, along with a young man and woman who look to be in their late 20s. I was intrigued to notice that these two share a last name, Kerri and Pirkko Eskola. As it turns out, the Eskolas are a Finnish couple who worked at the Lawrence Radiation Laboratory for 4 years in the late 60s and early 70s, contributing, along with Jim Harris, to the detection of 2 superheavy elements. They have since returned to Finland, and today they live in Helsinki, which is where I reached them last month.
The dial number is incorrect. Please try again.
Eventually. Chemical and Engineering News, this is Kerri.
This is Kerri.
I'm so glad to hear your voice. Kerri and Pirkko joined the search for new elements in the late 60s, moving from Finland to California with their 1-year-old daughter. And although they enjoyed the environment, they could sense unrest in the area of California around Berkeley.
You may know that Berkeley was a very restless place. There were riots, and so it was a restless place.
The area was a hotspot of activism at the time. On May 15, 1969, known as Bloody Thursday, a clash between protesters and police left 1 student dead. Dozens of officers and Berkeley residents were injured. Governor Ronald Reagan declared a state of emergency, bringing National Guard troops armed with rifles and bayonets to Berkeley. Against that backdrop of violence, the Finnish scientists found calm in focusing on their work.
It didn't really concern too much as we could see these rioting people in downtown Berkeley, but we were working up at the hills.
For Kerri, this meant some long nights running experiments at an instrument researchers called HILAC, short for Heavy Ion Linear Accelerator. It's there that the team would bombard their targets and gather the data that might reveal a new element had been created.
The accelerator doesn't know what hours it was valuable time. It ran all day and night. I worked all evening until about midnight, and then on some other times I would work overnight, stay at the lab.
That sounds like it could be very exhausting work.
Well, you get used to it, and it's when you're interested in what you are doing, then it's okay. As a scientist, I was of course always interested in finding new things, discovering things that were not known before, and this was a good opportunity to do it. So that's part of the excitement, I think.
Pirkko worked more regular hours, enabling her to care for the couple's young child. She focused on data handling, analyzing the results from the atom-smashing experiments.
Once they had finished the measurements, I got the data, and then I started my work.
In 1969, data from the experiments were stored on tapes, which were then brought to the lab's big computer to be analyzed using special programs. What the team hoped to see was something in the results that they couldn't explain. Superheavy elements, when created, decay almost immediately, in a matter of minutes, seconds, or less, too quickly to take a physical measurement of the atom. But the way in which these atoms decay is distinctive. They emit certain recognizable particles as they break down into smaller atoms, and scientists can identify the presence of a new element by looking for that characteristic decay pattern.
So if you were the one analyzing the data, were you the first one to know if something was working or not?
Well, in a way, but I was also kind of behind, so it was like 2 weeks behind before I could tell them that there was something. They were doing the experiments, and then it took me some time until I was ready to tell that there is something.
It was the combination of californium-249 with a carbon projectile that yielded that something. After some additional experiments to confirm that what they saw was due to the decay of element 104, the team submitted the finding to physical review letters.
It was a great feeling, yes. We celebrated this at the lab when we sent the paper off.
It's at that celebration that the photo with Jim Harris was taken. But that wasn't the end of the team's work. After the researchers announced they had found element 104, they began searching for element 105. And this time, they were using more advanced equipment, thanks to group leader Albert Ghiorso, whom Kerri describes as a real, continuous improvement type.
He never stopped improving things. It was obvious that he was not satisfied. He thought that if something can be done even better, if there is another better way of doing it, then we'll try it.
Ghiorso and his team coaxed the instruments to new levels of efficiency by building on the experience of their earlier experiments. But electrical engineering and atom smashing weren't the only things on Ghiorso's mind. Kerri and Pirkko remember their group leader as having a strong artistic streak, constantly doodling and even hanging his artwork in the lab.
There was lots of paintings around the laboratory on the walls. It was kind of funny looking because there was nice paintings around all this fancy equipment.
Both shared fond memories of their time in Albert Ghiorso's lab in California.
It was the most active time in my professional life and most satisfying time.
To live in California, to search the beauty of that nature, to see that corner of the world, those were very rich years for us.
Kerri and Pirkko left Berkeley after 4 years and returned to Finland, their names attached to 2 new elements. One, Rutherfordium, element 104, as we've already heard. And I think it's time for us to find out the name of the other element that they searched for with Jim Harris.
Okay, question 5. James A. Harris co-discovered element 104, Rutherfordium. He also co-discovered dubnium.
It's dubnium, actually. There was some controversy about the naming of these 2 elements, with the Berkeley team and a team in Russia both laying claim to making them first. The International Union of Pure and Applied Chemistry gets final say in these matters, and that group allowed the Berkeley team to name element 104, they chose Rutherfordium, and the Russian team named element 105 dubnium after the city of Dubna, where their experiments to synthesize it had been done. It's not uncommon for proposed element names to provoke debate among scientists, especially when professional rivalry is involved. To help promote consistency, IUPAC traditionally upholds a series of guidelines for naming new elements. An element can be named after a property of the element, a place, or a scientist, for example. And traditionally, elements have been named after scientists only after the scientist has died. But on today's periodic table, there is an element whose namesake is very much alive today, and that scientist happens to be the subject of one of our trivia questions.
Okay, question 4. I'm in the crowd now. Watch out. In 2016, the International Union of Pure and Applied Chemistry recognized the names of 4 new elements. Neonium, muscovium, and tennessine were named after locations. The 4th was named after a nuclear physicist. What is that element?
So now we've moved towards some of the freshest additions to the periodic table. These elements haven't been around for very long, but at least one person at Pub Trivia thought he had the answer. C&EN multimedia editor Matt Davenport, in the audience with a microphone, could sense the confidence.
I was eavesdropping. Did you say that you know the answer to this one? Oh, that's awesome. Oh, goodness.
That was Bernardo Schmidberger from Brazil, confidently stating oganesson. Let's see if he's right.
Question 4. In 2016, IUPAC recognized 4 elements. The one that I did not mention was oganesson in the very last column, and the noble gases.
Nice job, Bernardo. Element 118, named Oganesson and located at the very bottom right of the periodic table, is named after Yuri Oganessian, who is scientific leader of the Laboratory of Nuclear Reactions at the Joint Institute for Nuclear Research in Dubna, Russia, where the experiments to detect it took place. I managed to catch him during a rare gap in his busy travel schedule, and he told me he sees a relationship between the modern effort to identify new elements and the ancient practice of alchemy.
Alchemists, they were the first who wants to make gold from the lead. They want to really transform the element from one to another one. But they not succeeded. If you want to change the element, you have to change the nucleus. When the alchemists, attacked mostly from electron shell. To change the nucleus, it takes much more energy.
The energy provided by a modern-day cyclotron enables scientists to succeed in creating new elements where ancient alchemists failed. And a new accelerator now nearing completion in Russia will operate at even higher energies, perhaps enabling the identification of even more new elements. For now, though, Yuri's element namesake holds the distinction of being the heaviest element known. Yuri said he's thankful to his colleagues for putting his name on the periodic table, but he did confess that although 118 is named after him, it's actually not his favorite element.
I like 115 because 115 was really very interesting, became what, and we learn very much and more than from 118.
Element 115, as well as 118, came out of a long-term collaboration between scientists in Russia and scientists at Lawrence Livermore National Laboratory in California. During the course of those experiments, rotating teams of scientists from Livermore would travel to the lab in Dubna, where the months-long experiments took place. Although these 21st century scientists had the benefit of advanced equipment and new techniques, a key aspect of this work had not changed since the late 60s.
We really didn't expect to see anything because it is a long shot.
That's Nancy Stoyer, who was a member of the Livermore team along with her husband, Mark Stoyer. The two would make the necessary trips to Russia separately, staying a week or 10 days at a time, while the other stayed behind in California to care for their young child, who was 15 months old when the search for element 114 began in the late 1990s.
So basically, you're sitting there for 100 days throwing as many calcium nuclei at as many, in this case it was plutonium nuclei, that you can, put into a target for as long as you can, in the hopes that you'll get two to combine together and stick together and be able to then be detected in your detector system. And the probability for that occurring is just extremely low.
Just how low? Mark says a single experiment might involve shooting 10 to the 19 particles at a target made of 10 to the 20 or 21 particles, and that's with no guarantee of success. Scientists may run hundreds of hours of experiments just to get one interesting blip.
So the people that work in this field, I guess we're used to frustration. That you do these long experiments and you may or may not see something.
But researchers did see something in that first experiment.
When we saw this first event of interest, we were a little skeptical of it, and it's like, okay, we need to figure out what's going on here. We need to figure out what the probability is that this is something other than a random event.
Much like the effort to detect element 104 back in the 60s, the search for these newer elements also required sifting through a ton of data. Fortunately for this international collaboration, though, that data was no longer stored on tapes.
Because of the internet, the fantastic invention of the internet, we can get the data across the internet. So we were doing analysis in Livermore at the same time that they were doing analysis in Russia for all these experiments. We're working on it during our day here, which is nighttime there. So it's like somebody in the world is always working on this data.
The collaboration ultimately yielded reports of 6 new elements, from 113 to 118. I asked Mark if, after all of those new elements, the shine ever wore off on those moments of discovery.
For me, it still feels new and exciting. I kind of liken it to gold fever. If you go out and you're looking for gold and, panning for gold and you find a little bit, you get excited, right? And you want to find a little bit more. And so you keep panning, or you keep working, or you figure out how to do something a little better to find the gold. So it's a little bit like that. Try to find something maybe that hasn't been seen before, and then for a little while, there's only a small group of people on the planet that know that particular thing.
So we've just heard stories from the scientists behind elements 104 and 105, the first of the superheavy elements, and we explored the rare story of an element named after a living scientist. We're going to take a quick break, and when we come back, we'll jump back into the early days of the superheavy series and hear about another chemist whose contributions were judged significant enough to name an element after him while he was still alive.
Hey everyone, Doria Reister here. I'm C&EN's audience engagement editor, and I'm here to tell you about a great way to stay up to date with all the fascinating stories C&EN has planned for the International Year of the Periodic Table, or IYPT as we like to call it. It's our newsletter. Every week in your inbox, you'll get not only the latest news, but also some really cool extra content, such as periodic graphics, which are in collaboration with Compound Interest, or Chemistry in Pictures, which features submissions from you guys. You can sign up for our newsletter at bit.ly/chemnewsletter. Just point us to your inbox and we'll take it from there. Again, that link is bit.ly/chemnewsletter. We'll also include that link in this episode's description. Now, back to the show.
Question number 8. Which element is named after a former American Chemical Society president? You have to know this one.
As it turned out, not a lot of people knew this one.
Was there any question that you thought was really hard? Anyone want to take that?
ACS president question.
Yeah, the ACS president question.
I'm hearing that from a lot of people. What did you end up guessing?
Berkeley.
Berkelium. Interesting choice because the actual scientist worked at Berkeley, but unfortunately not the correct answer. Let's have Manny set us straight.
Which element is named after a former ACS president? Seaborgium. Of course.
Glenn Seaborg was the president of ACS in 1976, the Society's centennial year. He was a Nobel laureate, he advised presidents on nuclear policy, and he hatched the idea of placing the actinides, 15 elements with atomic numbers from 89 to 103, in a separate group in the periodic table based on their similar properties. And he helped discover several elements, including element 106, which now bears his name. Element 106 was somewhat of a comeback for Glenn Seaborg, a return to research after spending the 60s serving as head of the U.S. Atomic Energy Commission, and a return to the lab at Berkeley, which is where he had spent his early career. Seaborg began his work there as a graduate student, not long after the lab's new cyclotron was brought online.
He was very fortunate in the timing and the time that he got to Berkeley. As a graduate student, that the cyclotron was so new. He really benefited because the place was full of physicists, and he was practically the only chemist.
That's his son, Eric Seaborg, who collaborated on his father's autobiography and holds decades of his father's daily journals.
And so when people would bombard things in the cyclotron and come out with these materials that they didn't know, samples or materials that they didn't know what was in them,
that might include some particles the scientists were trying to make, plus their decay products and other atomic detritus from the collisions. All that extra stuff could make it difficult to see the elements of interest, so scientists would want to eliminate those contaminants using a variety of chemical techniques.
Sometimes he would be given the job of making the separations because you needed to know chemistry to do that. And that was kind of the key to what really started his career.
I asked Eric if he had any insight on what personality qualities made his father so successful.
When he first got to Berkeley as a young man, and he'd always been very successful academically and kind of at the top of his class and that sort of thing, and he got to Berkeley and he thought, oh my gosh, there's all these people who are just incredibly smart, and it's really hard to keep up with them. But he just resolved that if he ever failed, it would not be because he didn't work hard enough, that he was just going to always be prepared and always work hard.
Seaborg's hard work earned him the respect of many of the scientists he worked with. Some of them were such great supporters that they petitioned IUPAC to break with its tradition to name elements after scientists only posthumously and dub element 106 Seaborgium. And they were eventually successful.
He was just completely bowled over and really honored, and he used to talk about this as a bigger honor than a Nobel Prize because it's there forever.
One of the people instrumental in convincing IUPAC to change its tradition was nuclear chemist Darlene Hoffman. She helped confirm the detection of that element and, as it happens, also co-authored a book with Glenn Seaborg and Albert Ghiorso about their work in that section of the periodic table. I reached Darlene, now 92, at her home in California.
Well, for one thing, he was a wonderful mentor for me. When I first came to Berkeley, he was instrumental in getting me to come to Berkeley, and I thought if anyone deserved to have an element named after him, it would have been Glenn Seaborg.
The element that would come to be known as seaborgium was just one of the many heavy elements Darlene studied. In addition to carrying out rare chemical studies of superheavy elements, she and her colleagues also detected trace quantities of a plutonium isotope in rock from Southern California, contrary to scientists' long-held belief that elements heavier than uranium did not occur in nature. And she contributed significant discoveries about the nature of nuclear fission, including the influence of mass numbers on the fission behavior of fermium isotopes. She's a highly regarded nuclear chemist whom many scientists think should have won a Nobel Prize. But she told me that when she started college, she had a different path in mind.
When I went to college, I didn't know whether I wanted to take applied art or science, mathematics, which is a rather weird combination. And I started out in applied art, and I couldn't stand it.
Having decided applied art wasn't for her, Darlene announced to a teacher that she was switching to chemistry.
And so when I told her I wanted to switch from applied art to chemistry, she said, well, do you think that's a suitable profession for a woman? And my answer was, well, of course, look at Marie Curie.
After earning her PhD and completing stints at Oak Ridge National Lab and Los Alamos National Lab, Darlene accepted a position at Berkeley studying heavy elements. Chemistry, it turns out, was the right choice for her.
I enjoyed almost everything about it because you were finding things that nobody had, at least in this planet, nobody had ever seen before or ever measured before. And so it was all new and a new frontier.
That idea of being on the leading edge of chemistry came up a lot in my conversations with researchers. For me, it's hard to grasp the appeal of performing these endless, complicated experiments only to create something that fades away in an instant that you will never see or hold in your hand. I brought this question to two veterans of the search for new elements at Oak Ridge National Lab, which today makes radioactive targets like curium-248 and berkelium-249 for the ongoing work to synthesize elements 119 and 120. James Roberto, recently retired, and Krzysztof Rikaszewski were among the researchers who made elements 115 and 117, and both spoke of the value of pushing chemistry to new frontiers. Superheavy elements may not last very long, but some of their decay products have lasted long enough to do chemistry on, and that helps researchers probe the limits of what atoms can do. Here's James.
We don't know the heaviest nuclei that can be made. We don't know what the nuclear and electronic properties of those atoms might be. Will these be interesting new properties that will teach us more about science and that might eventually in the future have technological importance?
Although there are no practical applications for these new elements today, scientists hope that by pushing the list of known elements to higher and higher atomic numbers, some of those future materials may have useful applications. As Krzysztof noted, it wasn't until well after plutonium was first isolated that it found an application in nuclear batteries, which today provide power for spacecraft.
If you have to power your mission to Mars and power some equipment there, you are sometimes using radioactive isotopes. If you asked this question 50 years ago, there were no good applications, except making maybe a bond and energy, and now we are 14 atomic numbers up from this region. So they will be applications sooner or later.
In the 1960s, physicists predicted something called the island of stability, a region where new superheavy elements with certain combinations of protons and neutrons might last much longer than any of their predecessors, long enough to enable scientists to study their chemical and nuclear properties, and potentially long enough for practical applications. Today, scientists feel they are on the shores of that island of stability. They've seen a stabilizing effect from adding neutrons to isotopes of elements 112 and 113, for instance. And they think the trend could continue in isotopes that haven't yet been synthesized. But even without practical applications for these atoms today, scientists see value in what insight these elusive elements may offer for the atoms that exist outside the cyclotron. Here's Nancy Stoyer from the Livermore group that helped make the newest superheavy element, element 118.
The physics that holds the nucleus together for all of the elements, all the atoms that are within our body is the same physics that holds things together at these extremes. And it's a matter of understanding, nature and why are things the way they are. A fundamental quest for knowledge on why is the world the way it is.
We want to offer special congratulations to the Knights Who Say Nitrogen, the winning team from IYPT Pub Trivia. And props to C&EN reporter Tian Wen, who wrote every single one of those pub trivia questions and also helped to produce this episode. Keep an eye out for more on the creation of superheavy elements coming from C&EN's multimedia department later this year. Next month on Stereochemistry, C&EN reporter Sam Lemonick takes a deep dive into efforts to use underwater drones to monitor the chemistry of the entire ocean. You can subscribe to Stereochemistry on iTunes, Google Play, and TuneIn. Stereochemistry is a production of C&EN, the news magazine of the American Chemical Society. This episode was written and produced by me, Kerri Jansen. It was edited by Lauren Wolfe, Matt Davenport, Amanda Yarnell, and Sabrina Ashwell. The music you're listening to now is Rewound by Chris Zabritsky. Our ad music was Plain Loafer by Kevin MacLeod. Thanks for listening.